In this lecture, we're going to talk about hashing, and we're going to describe a popular technique called Bloom filters. Before we get into hashing, we're going to talk about a toy problem, balls into bins. We're going to throw balls randomly into a set of bins. We'll do some simple probabilistic analysis of this problem, and this will give us some intuition about the design of hashing schemes. One of the neat ideas we're going to see with the balls and bins problems is the power of two choices. This is going to motivate some of our more sophisticated hashing schemes. After we look at the toy problem, balls into bins, then we'll look at the traditional hashing scheme, chain hashing, and then we'll look at our more sophisticated scheme, Bloom filters. So let's dive into the balls into bins problem. For this toy problem, we have n balls, which are identical to each other, and we have n bins, which we'll label B1, B2, up through Bn. Each ball is thrown into a random bin, and this is done independent of the other bins. Now what we're going to do for this toy problem is we're going to throw each ball into a random bin. Now the process for each ball is independent of what happened for the other balls. We want to look at the number of balls that are assigned to each bin. Therefore, we look at the random variable load of I, which is the number of balls assigned to bin I. What we're interested in is the maximum load. This is the maximum number of balls in any particular bin. In other words, the max load is the max over I of the load of bin I. How large can the max load get? Well, in the worst case, all of the balls might get assigned to the same bin. But what's the chance of that? It's quite small. I mean, what's the chance of all n balls being assigned to bin B1, let's say? The probability of one particular ball being assigned to bin B1 is 1 over n. What's the chance that all n balls get assigned to this particular bin? It's 1 over n to the n. This is really tiny, so this is very unlikely. In the worst case, the max load could be n because of such a scenario. But what is the typical scenario? How large is the max load typically? That's what we want to analyze now. We want to make a statement such as, with high probability, the max load is some quantity such as square root n, log n, order 1. So let's dive in and see what the max load is in a typical scenario. Let's take a short probability quiz to give a quick refresher on some basic probability. Let's look at what is the probability that the first log n balls are assigned to bin Bi for a particular I. We want to look at the probability that the first log n balls are assigned to this particular bin. Go ahead and write the quantity here. Now the solution is 1 over n to the log n. Why is that? Let's look at it more closely. Take a particular ball, J. What is the probability that this ball is assigned to this particular bin, Bi? Well, the ball is going to a randomly chosen bin, so the chance of going to any particular bin is 1 over n. Therefore, the first ball has probability 1 over n of being assigned to bin Bi. The second ball, same, has probability 1 over n of being assigned to bin Bi, and so on for all of these log n balls. So the probability that all of them are assigned to bin Bi is the product of 1 over n. For each. So the total probability is 1 over n raised to the power log n. Now let's dive into the analysis of the maximum load. What we've seen so far is that for a particular set of log n balls, the probability that these log n balls are assigned to a particular bin, Bi, is 1 over n raised to the power log n. We're going to try to show that the max load is typically, at most, log n. Now what does typically mean? We're going to have to detail exactly what we mean by that. But in order to prove that the max load is the most log n, we want to show that the probability that a particular bin, Bi, gets load greater than log n, and we want to upper bound that probability and show that it's small. It's unlikely to get load at least log n. In order for a bin, Bi, to get load at least log n, a particular set of log n balls have to get assigned to bin Bi. Now it may be more than log n balls that get assigned to Bi, but we know that there's at least log n balls that are assigned to Bi. So we're going to get an upper bound on this probability. First, we have to choose the particular set of log n balls that are going to be assigned to bin Bi. How many ways are there of choosing log n balls? There's n choose log n. Now, for this particular set of log n balls, what's the chance that they are all assigned to bin Bi? Well, that's what we bounded before. That's 1 over n raised to the power log n. Now, what happens for the other n minus log n balls? Well, some of them might get assigned to this bin Bi as well, in which case we may be counting these events multiple times. So we're getting upper bound on this probability. Notice that if we had an extra term here, which is 1 minus 1 over n raised to the power n minus log n, this is saying that all of the other balls, besides these log n balls that we chose, are assigned to other bins. So what is the probability that a particular ball is not assigned to bin bi? That's 1 minus 1 over n. We have n minus log n balls that are not assigned to bin bi. Then what is this bound? This is actually equal to the probability that this bin bi gets load exactly log n. But that's not what we want to bound. We want to bound the probability that the bin gets at least log n. So we want to get an upper bound. We ignore where the other balls, the other n minus log n balls are assigned. And then we get an upper bound on the probability because we allow these balls, these n minus log n balls, to be assigned to any bin, maybe bi or maybe a different bin. Now let's try to get a handle on this term. N choose log n. Let's look at it more generally. N choose k. Recall, what is n choose k? It's n factorial over n minus k factorial times k factorial. If we expand this out, we got n factorial on the numerator, but all the terms from n minus k downwards cancel out with this n minus k factorial in the denominator. So we get n times n minus 1 down to n minus k plus 1. The remaining terms, again, cancel with this n minus k factorial in the denominator. And then also in the denominator, what are we left with? We're left with k factorial, which is k times k minus 1 times k minus 2, and so on down to 1. Let's try to get a handle on this quantity. Notice the first term is n over k. The second term is similar. It's n minus 1 over k minus 1. If n is big, that's pretty similar to n over k, and so on. So we have n over k, n minus 1 over k minus 1, and so on down to n minus k plus 1 over 1. So there's k quantities, k ratios there. So here are the k ratios. Each one, let's say, is approximately n over k. So this is approximately n over k raised to the power k. Actually, this approximation is not too bad of a bound on this quantity. What one can show using Stirling's formula is that n choose k is at most n times e over k, all raised to the power k. So if we put an extra factor of e in the numerator, then we get a rigorous upper bound on n choose k. And that's what we're aiming for. We're aiming for an upper bound on the load size of bin bi. So we can upper bound n choose log n by using this formula. So plugging in this bound for our case, we have k equals log n in our scenario. So we get the upper bound n times e over log n raised to the power log n. That's for the n choose log n. And then we still have this term 1 over n to the log n. 1 over n to the log n. Now these are both raised to the power log n, so we can cancel out this n with this n. So what are we left with? We're left with e over log n raised to the power log n. Now notice the denominator is growing with n, whereas the numerator is a fixed constant. So as n grows, this becomes smaller and smaller. We're going to look at this asymptotically as a function of n, so we can bound this inner term by any fixed constant we want. So let's bound it by the constant 1/4. So we're going to say e over log n is at most 1/4, and so we get this whole quantity is bounded by 1/4 to the log n. Now what is the bound that we used here on n? We used the fact that log n is bigger than 4 times e. When is that true? That's true when n is big enough. In particular, if n is bigger than 2 to the 11th, then log n is bigger than 4 times e, so we can replace e over log n by 1/4. Now what is the nice thing about using 1/4 here? Well, assuming that the log was base 2, then this quantity, 1/4 raised to the log n, is equal to 1 over n squared. So in summary, we've shown that the probability that bin bi gets load at least log n is at most 1 over n squared, which is tiny as n grows. Now what we saw on the last slide was that the probability that a particular bin bi gets load at least log n is at most 1 over n squared. Now, can we use that to bound the max load? Can we upper bound the probability that the max load is at least log n? Why don't you go ahead and write this quantity here. If you have trouble doing it, don't worry, we'll go through it in a minute. Now we want to bound the probability that the max load is at least log n. That's the quantity here. In order for the maximum load to be at least log n, at least one bin, maybe several, have to have load at least log n. In order to upper bound this probability, we can use our earlier analysis. We know the probability that a particular bin gets load at least log n is at most 1 over n squared. So now, in order for at least one bin to get load at least log n, let's look at all the choices for the bins. So we can sum over each bin, and then we can look at the probability that the load in bin bi is at least log n, which is what we bounded right here. That's at most 1 over n squared. There are n choices for the bin, and for each particular bin, the probability the load is at least log n is at most 1 over n squared. And this is 1 over n, which proves the result that the max load is at least log n with probability at most 1 over n. Now we want to look at the complementary event that the max load is strictly less than log n. What is the probability of this? Well, this event is unlikely to happen. This happens with a small probability. This is going to happen with a large probability. In particular, it happens with probability at least 1 minus 1 over n. And in fact, one can do a similar analysis a little bit more carefully, and you can show that the max load is theta of log n over log n. So we can get an upper bound and a lower bound, which are within constants of each other. So instead of an upper bound of log n on the max load, we can get a slightly better bound of log n over log n. And this error probability can be boosted from 1 over n to 1 over n squared, or 1 over n to the 10th, any polynomial in n we can get here by changing the constant up front. And when this error probability is 1 over a polynomial in n, we say that this event happens with high probability. In particular, if it happens with high probability, then that means it happens with probability at least 1 minus 1 over some polynomial in n. And we can make this polynomial as small as we want by increasing this constant out front. Now let's look at the following twist on the balls and bins problem. This is going to be a better approach, better in the sense that it's going to reduce the max load. Now in the previous balls and bins problem, each ball was going to a random bin and it was independent of the assignment for the other balls. Therefore, we could have assigned all the balls simultaneously, in parallel. They could have all been assigned to bins at the same time. Or we could have assigned them one by one, sort of sequentially. So we could have taken ball 1 and assigned it to a random bin, take ball 2, assign it to a random bin, and so on up to ball n. That's what we're going to do here. We're going to assign the balls sequentially, and we're going to look at a slight twist of the other scheme. So let's go through the balls from 1 through n. Index I will correspond to the current ball that we're considering. In the old scheme, we choose one random bin, say j, and we assign the ith ball to bin bj. Now in the new scheme, what we're going to do is we're going to choose two random bins, say j and k. Now, which bin are we going to assign the ith ball to? Well, we're going to assign it to the better of these two bins. What exactly do we mean? We mean the one which has smaller load. So, let load of j and load of k denote the current load in these particular bins, bj and bk. And we're going to assign this ith ball to the least loaded of these two. So if the load of bj is strictly smaller than the load of bk, then we assign the ith ball to bin bj. And in the other case, we assign the ith ball to bin bk. So the ith ball is going to the least loaded of these two bins. This new best of two approach is a simple twist on the original approach. What are we doing now? Well, instead of choosing a random bin, we choose two random bins, and we assign the ith ball to the least loaded of these two random bins. It turns out that with this scheme, the maximum load is order log n with high probability. Recall that the previous approach had max load on the order of roughly log n, and we've reduced it from log n to log n just by, instead of choosing one random bin, we choose two random bins, and we send to the best of the two. This is a substantial gain because log n is quite small, even for a very large n. So this is almost like order 1. It's very close. It's a very small quantity. Well, after seeing this result, you might say, well, why choose two random bins? Let's choose three random bins, and maybe we'll get log n. Well, it turns out that the big gain is from 1 to 2, and after that, there's not much gain. In particular, if you choose D at least two bins, so instead of choosing two random bins, you choose D random bins, and you assign the ith ball to the least loaded of all of these D bins, then the max load is going to be log n over log D. So the improvement with D is very small. Now keep this idea in mind later, this idea of choosing the best of two choices. We're going to use this intuition later to get better hashing schemes, and then to drive the intuition behind the Bloom filters. So finally, let's dive into hashing. Now let's turn our attention back to hashing, which is our main focus. It'll be useful to keep a running example in mind to motivate our various hashing schemes. The example we'll use is unacceptable passwords. We want to maintain a database of unacceptable passwords. For example, these might be words that are in the dictionary. Now the setting is that a user will enter a proposed password, and our system should quickly respond if that proposed password is acceptable or not. So we need to quickly check whether the proposed password is in the database of unacceptable passwords or not. Now let's formalize our setting a little bit more precisely. We have a huge set U, which is the universe of possible passwords. Now this is an enormous set. For example, if we simply look at passwords as strings or words of length 8, then this set is of size 52 to the 8. Hence, this set U is too large to maintain. Instead, we're going to maintain a subset of this universe, which we'll denote as subset S. S will contain the set of unacceptable passwords. The main operation our data structure needs to perform are queries. So for an element X in our universe, so X is a proposed password in this setting, is X in this subset S? So is X an unacceptable password? Now we want to build a data structure or hashing scheme which answers these queries quickly. Let's first look at how the traditional hashing scheme, known as chain hashing, works in this setting. Now in order to maintain this set S, we're going to use a hash table H of size n, little n. In chain hashing, this table H is an array of linked lists. We're going to use a hash function little h, which maps elements in U to elements in H. So each of the possible passwords is mapped to one of these n bins by little h. Now to insert an element into this subset S, we simply find its hash value, then we go to that bin, and then we add the element onto the linked list at that particular location. And then to do a query, we simply go to the hash value, and we look at the linked list to check whether it's there or not. For each element of the universe, little h of X maps to one of these n bins. Now we're going to analyze random hash functions. So we're going to assume that h of X maps to a random bin. Moreover, we'll assume this choice, this random map, is independent of all other hashes. So where h of X maps to is independent of where any other element of the universe maps to. So this little h is a completely random hash function. Now if you think of this hash table as bins, and you think of these elements in S as balls, then what this hash function is doing is it's assigning these balls into random bins. So it's reminiscent of our balls into bins problem that we analyzed before. Now it'll be useful to have a little bit of notation before we move on. This set U is huge and will denote its size by capital N. The hash table will denote its size by little n. Now capital N, as in RSA, will be exponential size in little n. And we'll use little m to denote the size of this database, capital S, that we're maintaining. And once again, capital N is much bigger than little n, and typically our hash table size is at least the size of the database we're maintaining. So little n is at least size m. And our goal, of course, is to try to maintain this database as not much larger than little m. Once again, in the traditional hashing scheme, chain hashing, H, our hash table, is an array of linked lists. H is an array of size n, and H of I, the ith element of H, is a linked list of elements in our subset S which map to I. So in other words, H of I is a linked list of those elements, of those unacceptable passwords whose hash value is exactly I. Let's look at the query time. How long does it take us to answer a query of the form, is X in the subset S that we're maintaining? Now in order to answer this query, what we have to do is look at the hash table at the index I, which is H of X. And then we have to go through that entire linked list and check whether X is in there in that linked list or not. So the time it takes us is proportional to the size of this linked list. What's the size of this linked list? It's the load at this bin. If we think of the elements of S as balls, these are getting assigned to bins, which are their hash values. The time it takes us to answer a query is proportional to the load size at the hash value. Let's introduce some notation. Let m be the size of our dictionary of unacceptable passwords, and let little n be the size of our hash table. So in our balls and bins analogy, little m is the number of balls that we're throwing in, and little n is the number of bins. Now if m equals n, so the number of balls is the same as the number of bins, this is the toy problem that we analyzed before. And what we saw is that the max load is order log n with high probability. Of course, in the worst case, it might be order n, or n might be the max load, but that's an unlikely event. With high probability, the max load is going to be order log n, which means then the query time in the worst case is going to be order log n with high probability. Now when n is huge, then order log n might be too slow for us. So how can we achieve faster query time? Well, one way is to try to increase the size of our hash table. In order to decrease this max load from order log n to order 1, so that the query time will be order 1, constant time queries, we're going to have to increase the size of the hash table from order m to order m squared. Now that's quite a large price to pay, so let's see if there are simpler ways to achieve reductions in the query time. Now our intuition for the following scheme comes from the balls and bins example from before. This is the simple scheme that we use right now. We're sending n balls into n bins. Each ball is going into a random bin. What did we use to improve that balls and bins scheme, to improve the max load? Well, we used the two-choice scheme. And what we saw is that the max load goes down to order log n when we allow each ball to go to the least loaded of 2 random bins. So let's try and use a similar scheme now for hashing. What we're going to do now is instead of using a single hash function, we're going to choose a pair of hash functions, h1 and h2. Each of these hash tables maps elements of view of our possible passwords into our hash table of size n. Now we'll assume that these hash functions are random, so each element acts in the universe of possible passwords maps to a random element of the hash table. h1 of x is random, h2 of x are random, and these are independent of each other and independent of the other hash values. The first question is, how do we insert an element, a possible password, into our dictionary of unacceptable passwords? In the traditional scheme, this is quite straightforward. What we do is we look at our hash function, and we look at h of x, that tells us the hash value, and now we looked at the linked list at h of x, and we add element x onto that linked list. But now we have 2 hash functions, h1 and h2. So how do we do this insertion into our dictionary in this scenario when we have 2 hash functions? This is a bit of an open-ended question, but why don't you think about how you would insert an element into our dictionary using 2 hash functions? Let's go ahead and look at how we do this insertion. We want to insert this element x into our dictionary of unacceptable passwords. First thing we do is compute these 2 hash values. So we compute h1 of x and h2 of x. Think of our balls and bins analogy. We have this ball x, and what we've done is we've chosen 2 random bins, h1 of x and h2 of x. Which bin do we add the ball x into? We add it into the least loaded of these 2 bins. What is the load of the bin? It's the size of the linked list. We can maintain the size of each of these linked lists so that we can quickly determine which of these 2 is least loaded, and then we can add in x into that appropriate linked list. And then we can increment the size of that linked list. So this can all be done in order 1 time for an insertion. The next question is, how do we do a query? How do we check whether an element y, a proposed password y, is in our dictionary of unacceptable passwords? We start off the same as an insertion. We compute the 2 hash values, h1 of y and h2 of y. These are the 2 possible locations for y. We have no way of determining which of these 2 locations it might be in, if at all, because we have no way of determining what the dictionary looked like at the time that we inserted y, if we did insert y. So what do? We check both bins. We check the linked list at h1 of y, and we check the linked list at h2 of y, and we look for y in both of these linked lists. So we check the linked list at h of h1 of y, and we check the linked list at h of h2 of y. And we look in both of these linked lists for the element y. If it's in either of these linked lists, then we know that y is in the dictionary. If it's in neither of these linked lists, then we know that y was never inserted into our dictionary of unacceptable passwords. So how long does it take to do a query? Well, the query time now depends on the load at this location and the load at this location. So if we have an upper bound on the maximum load, then the query time is twice the maximum load. Now if m equals n, so the size of our dictionary of unacceptable passwords and the size of our hash table are the same, then what we know from our balls and bins analogy is that the query time, the max load, is going to be order log n in this scenario. So just changing from one hash function to a pair of hash functions and using this scheme, then our query time goes down dramatically from order log n to order log n. And there's no extra cost in terms of the space. Though there is a question about how we maintain this hash function h, especially if it's a truly random hash function. In practice, we can't store a truly random hash function. Instead, we use pseudo-random hash functions. So we use a hash function which we obtain from a library such as rand or drand48. But for the purposes of the analysis, it's convenient to consider a truly random hash function so that we can do this nice analysis such as how we obtain the order log n max load for the m equals n case for the simple case of one hash function. We skipped the analysis for the case of the balls and bins example where we did the two choices, where we had each ball going to the best of two random bins. In that case, we claim that the max load is order log n. That analysis is reasonable to do, but it's much more complicated, so we skipped it in this lecture. Now this completes our description of the traditional hashing approach, the chain hashing. Now we can move on to the Bloom filters. Now we can finally describe Bloom filters. Let's keep in mind this running example from before, the case of unacceptable passwords. We're going to describe a new data structure that has faster queries. Recall in the traditional hashing scheme that we previously described, the query time was order log n for the simple scheme, or order log n for the more advanced scheme which used the power of two choices idea. Here we're going to achieve query time order 1, so constant query time. And this is guaranteed. Recall that the other query times were probabilistic statements. So with high probability, the query time was order log n or order log n. In the worst case, it was order n. But here, it's guaranteed to always be constant query time. This data structure will be very simple, and it'll use less space than before. There will be no linked lists or anything like that. It'll just be a simple binary array. Now, there are a lot of benefits. It's simpler, less space, faster queries. Now, there must be some cost for this simplicity and this faster time. So what is the cost? What is the trade-off for this scheme? Well, this scheme is not always correct. Occasionally, there are false positives. And this happens with some probability that we'll analyze. We'll try to figure out what is this probability of false positives occurring. What exactly do we mean by false positive? We have an element x, which is not in our dictionary of unacceptable passwords. So this is an acceptable password. But our algorithm occasionally says, yes, this x is in the dictionary. In this setting, false positives are acceptable. Why? Because we have an acceptable password, but we say that the password is unacceptable. It's in our dictionary. So we falsely say that the password is in our dictionary of unacceptable passwords. So somebody types in a password, and we say, no, that's not allowed. Ideally, it should have been allowed, but we said that no, it's not allowed. So then the user has to enter a new password. But in exchange for these false positives, we have guaranteed query time. So we answered the question of whether it was an acceptable password or not quickly. And in this setting, false positives are reasonable. False negatives, that would have been a big cost. That would have been unacceptable in this setting. When we have an unacceptable password, we definitely want to say it's unacceptable. If we have an acceptable password, okay. If we occasionally say that it's an unacceptable password, that's okay. So in this setting, it's reasonable to have false positives with some small probability that we'll try to bound. In other settings, it may be unacceptable to have false positives, in which case, Bloom filters might be a bad idea. So this is not a universal scheme. You have to look at your setting and determine whether the price of having a simpler and faster scheme is worth the cost of having false positives. Is it acceptable to have false positives with some small probability? What are the basic operations that our data structure is going to support? First operation is insert x. So given a possible password x, we want to add this password into our dictionary of unacceptable passwords. The second operation is a query on x. Is this proposed password in our dictionary of unacceptable passwords? If this proposed password is in our dictionary of unacceptable passwords, then we're always going to output yes. So we're always correct in this case. The problem is that when this proposed password is not in our dictionary, so it is an acceptable password, we usually output no. And we have to bound what we mean by usually. But occasionally, we're going to output yes. So when this proposed password is acceptable, Occasionally, we're going to have a false positive and say, yes, it is in the dictionary of unacceptable passwords. So this password is not allowed. So we have false positives with some small rate, and we have to bound that rate and see what it looks like. So now we have k-hash functions instead of just one, h1, h2, up to hk. We're going to initialize our hash table h, capital H, to all zeros. So all the bits, the n bits of h, are set to 0. How do we do an insertion? How do we add an element x, a possible password, into our dictionary S of unacceptable passwords? Previously, we computed its hash value, h of x, and we set that bit to 1. What are we going to do now? Now we compute the k hash values, and we set all of those k bits to 1. So we go through the hash functions 1 through k, and then we compute its ith hash value, and we set this bit to 1. It might already be 1, as before, but we always change bits from 0 to 1, just like before. How do we do a query? How do we check whether an element x was inserted into our dictionary S? Well, we compute its k hash values, and we check whether all of those k bits are set to 1 or not. If all of those k bits are set to 1, then our best guess is that x was inserted into the database S. If any of those are still 0, then we're guaranteed that x was not inserted into the database. So let's write that out more precisely. If for all of those k hash values, the hash function at those k bits is set to 1, then we output yes. We believe that this element x is in the database S. If any of these k bits is still 0, then we're guaranteed that this element x is not in the database. So we output no. Let's take a look at the correctness of this algorithm for our queries. Suppose x was inserted into our database S, and we do a query on x. What do we output? Well, when we inserted x into the database, we set all of these k bits to 1. So when we do a query, we're guaranteed that all of these bits are set to 1, and so we're going to output yes, because none of the bits ever change from 1s to 0s. Bits only change from 0s to 1s. It's a one-directional process. So if x was inserted into the database, when we do a query on x, we always output yes, it is in the database. Now suppose x was not inserted into the database, and we do a query on x. Sometimes we might say yes, we believe it's in the database, in which case we get a false positive. We falsely said that yes, it's in the database. How can this occur? This can occur if all of the k bits were set to 1 by other insertions. So for each of the k bits of x, so take the ith bit, so this is hi of x, there is some element z which was inserted into the database S, and one of the k bits for z is exactly matches the ith bit of x. Which of the k bits for z? Let's say the jth bit for z. So the jth bit for z matches the ith bit for x. In other words, hi of x, this is the ith bit for x, matches the jth bit of z. So hi of x equals hj of z. This means that when z was inserted into the database, we did the insert of z, then we set this bit, which matches the ith bit of x, to 1. And if this is true for every bit of x, so all of the k bits of x are set to 1 by some other insertion, then we're going to get a false positive on x. So this scheme has this extra robustness or redundancy. In order to get a false positive, we need all of these k bits to be set to 1 by some other insertions. Whereas the previous scheme only had one bit which we're checking. Now we have k bits which need to get set to 1 in order to get a false positive. So it seems like things improve, that the false positive rate goes down as k increases. But in fact, there's an optimal choice of k. If k gets too large, the false positive rate starts to shoot up again. Why is that? Well, if k is huge, then for every insertion, you're setting k bits to 1. So you're setting many bits to 1 if k is huge. So that means that for each of these insertions, each of these elements in S, they have many bits, many choices of j, which are set to 1. So it's more likely, if k is big, that one of these k bits is going to match up with one of the bits of x. So if k is too large, every insertion is setting too many bits to 1. If k is small, then when we're checking it, when we're doing a query on x, we're checking too few bits. So there's some optimal choice of k, not too large and not too small. What we want to do now is more precisely analyze these false positives. What's the probability of a false positive? We want to look at it as a function of k, and then we can figure out the optimal choice of k in order to minimize the false positive rate. And then we can compare and see what that false positive rate looks like to see whether this is a good data structure to use or not. Let's start analyzing the false positive rate. As before, let m denote the size of our database or dictionary that we're maintaining, and let little n denote the size of our hash table. Now, presumably, n, the size of our hash table, is going to be at least the size of the database that we're maintaining. So the number of bins is at least the number of balls that we're inserting. So the important parameter is going to be the ratio of these sizes. So let C denote this ratio, the size of the hash table compared to the size of the database. So C is going to be at least 1. And our goal is to try to get the smallest C possible. So once again, the size of our database, S, our dictionary of unacceptable passwords, is M, and the size of our hash table is C times M. There's a constant C, which is at least 1, and our hash table is this constant C bigger than the database that we're maintaining. Now, for an element X, which is not in our database, so we didn't do an insertion on X, let's look at the probability of a false positive for this X. So X was not inserted into the database, and what is the probability of a false positive? So we incorrectly say that X was inserted into the database. So in order for this to occur, we need that all of the k bits for X, so H1 of X, H2 of X, up to HK of X, were all set to 1. If all of these bits are 1, but X was never inserted into the database, then we'll get a false positive. We'll incorrectly say, yes, it is in the database because all of the k bits are 1, but it was never, in fact, inserted into the database. So let's try to analyze this probability that all of these k bits are set to 1. Let's first look at a simpler problem. For a specific bit, B, what's the probability that specific bit is set to 1? So for a specific bit B, this ranges between 0, 1, and n minus 1. What is the probability that this specific bit B is set to 1? It'll be slightly easier to look at the complementary event that this specific bit is set to 0. So the probability that this specific bit is 1 minus the probability that this bit is still 0. Now to analyze the probability that it's still set to 0, what we have to do is we have to check that all of the insertions miss this 1 bit. Now let's go back and think about our balls and bins analogy in order to analyze this probability. Now we have m insertions. In our simple hashing scheme, these insertions correspond to throwing a ball into a bin. So this corresponds to throwing m balls into bins. But notice for each insertion, we have k hash values that we look at, and we set k of these values to 1. So each insertion corresponds to k balls. So actually we're throwing m times k balls into bins. So we're throwing these m times k balls, and we're throwing them into n bins. Now what does this specific bit being set to 0 correspond to in this balls and bins example? In order for this bit to still be 0, we need that all of these m times k balls miss this specific bin B. So this probability that this bit is 0 is equivalent to the probability that all m times k balls miss this specific bin. For one ball, what's the probability that it misses a specific bin? The chance it hits a specific bin is 1 over n. The chance it misses this bin is 1 minus 1 over n. And we're doing this for m times k balls. Now this expression is not very complicated, but it'll be much more convenient for us to have a slightly simpler expression. So what have we done so far? We've shown that the probability that a specific bit is 0 is equal to 1 minus 1 over n raised to the power m times k. Let's try to manipulate this to get a slightly more convenient expression. I want to replace this by an exponential. Suppose I look at e to the minus a for a number a. Let's take a look at the Taylor series for the exponential function. Let me remind you of that expression. So I have the exponential of minus a, where a is a number. Let's start us off with 1 minus a, plus a squared over 2 factorial, minus a cubed over 3 factorial. Notice it's the alternating sign. Next term is a to the 4th over 4 factorial, and so on. You have this infinite series. Now for small a, this series is decreasing. And as a goes to 0, then this series is approximated by 1 minus a. So this is a good approximation when a is sufficiently small. That's going to correspond, in our case, to n being sufficiently large. And we're looking at asymptotics as n grows to infinity. So let's use this as an approximation to simplify our analysis of the false positive rate. So what can I do here? Here I have A equals 1 over n. As n grows, 1 over n goes to 0. So this is a reasonable approximation. So I can replace 1 minus 1 over n by e to the minus 1 over n. So I have e to the minus mk over n. Recall that C is the ratio of the size of the hash table to the size of the database. Therefore, this expression can be simplified to e to the minus k over c. So now I have a very simple expression for the probability that a specific bit is 0. Recall our original problem. We have an element x which was not inserted into our database. We want to look at the probability of a false positive for this element. So what's the chance we output yes, even though x was not inserted into the database? So what's the probability that all of these k bits corresponding to x were set to 1 by some other insertions? Well, the probability of a specific bit being set to 0, we've just analyzed and shown that it's approximately e to the minus k over c. So what's the probability one of these specific bits is set to 1? It's 1 minus the probability that it's set to 0. The probability set to 0 is e to the minus k over c. The probability set to 1 is 1 minus e to the minus k over c. And we want k specific bits all set to 1. So the probability of that is this raised to the power k. This expression is the false positive probability. It's not very nice right now because we have this k. Can we simplify this by eliminating k? Can we figure out what is the optimal k in order to minimize this false positive probability? Recall our intuition from before. We wanted to have k not too small. If k is small, then when we do a query, we're checking too few bits. But if k was big, if it's too large, then when we do an insertion, we're setting too many bits to 1 for each insertion. So there's some middle ground, and we want to figure out the optimal choice of k in order to minimize this false positive probability. So what are we going to do? We're going to take this function, we're going to take its derivative, set it equal to 0, and find the optimal choice of k in order to minimize this expression. So a bit of calculus. We're going to skip it, but I'll tell you the punchline. Recall the expression that we just obtained for the false positive probability. The expression was 1 minus e to the minus k over c raised to the power k. Let's look at this as a function of k. So let f of k denote this expression. This is f of k is a false positive probability for a specific choice of k, the number of hash functions. Our goal is to figure out what's the optimal choice for the number of hash functions in order to minimize this false positive probability. So what do? We're going to minimize this function f of k. How do we find the optimal choice of k? Well, we take its derivative, set it equal to 0, check whether it's a global minimum, and then we find that choice of k which sets the derivative equal to 0. Where does that optimal happen? It happens at k equals c times ln 2. That's the natural log of 2, the log base e of 2. I'm going to skip this calculus so that I don't embarrass myself. I've forgotten my calculus too, so don't worry. But let's look at this choice of k, which is the optimal choice in order to minimize the false positive probability. It's quite interesting. Actually, first off, let's plug this choice of k back into this expression, and then we can simplify it. Well, first off, when you plug in k equals c ln 2 over here, then the c's cancel and you're left with ln 2. And then on the outside, we have c ln 2. What is e to the minus ln 2? That's exactly 1/2. And what's 1 minus a half? It's a half. So the inside is 1/2 raised to the power c ln 2. Let's separate the c from the ln 2. So we have 1/2 to the ln 2, all raised to the power c. Now what is this inside? This is just a fixed constant. It's 1/2 raised to the power ln 2. You can plug it in on your calculator. Turns out that inner expression is 0.6185 approximately. So we have that raised to the power c. C is the ratio of the size of our hash table compared to our database. Now we have a simple expression for the false positive probability. It's 0.6185 raised to the power c. So if you tell me how large of a hash table you're willing to do, I can tell you what the false positive probability is. Before we look at that, let's just take a look at this expression right here. I want to point out something interesting about this choice, this optimal choice of k. What's the probability a specific bit is 0 or 1? The chance it's 1 is this inner expression. Chance it's 0 is this expression right here. Both of those are 1/2. So the chance we're setting a bit to 0 is 1/2. The chance we're setting it to 1 is 1/2. So what does this binary string look like after we've done m insertions? So it's a binary string of length n, and we've done m insertions into it. What does it look like? Well, each bit afterwards is set to 0 with probability half. So each bit is randomly set to 0 or 1. So this string h corresponds to a random string where each bit is independently flipped to 0 or 1. So what's interesting is that the optimal choice of k means that if we just look at what this random string looks like, it's going to correspond to a random binary string where each bit is independently set to 0 or 1. So the optimal choice of k corresponds to balancing out the zeros and ones in h, so that h looks like a random string. Recall our setting. We have a database of size m, and we have a hash table of size c times m for some c strictly greater than 1. What we just showed is that the false positive probability is approximately 0.6185 raised to the power c. This 0.6185 corresponded to 1/2 raised to the power ln 2. Let's now look at some specific examples to see how this performs. Let's suppose we did the naive scheme where k equals 1. So we didn't do the optimal choice of k. We just set one hash function. And let's look at the case where we do 10 times larger or 100 times larger. Now this expression for the false positive probability was assuming the optimal choice of k. In order to analyze this case where k equals 1, we have to go back to our expression of f of k. If you look back at that expression and you plug in k equals 1 and c equals 10 or c equals 100, you get the following. In the first case, the false positive probability is 0.095, and in the second case, it's 0.00995. Now suppose we do the optimal choice of k. So then our false positive probability is going to be this expression. Let's look at c equals 10. What do we get? We get 0.0082, a reasonable gain, but not that much better than c equals 100 with this simple k equals 1 case. Let's try c equals 100. So our hash table is 100 times bigger than the database we're trying to store. But this is just a binary string, right? So it's very reasonable to consider a hash table which is 100 times bigger. Now the false positive probability is 1.3 times 10 to the minus 21. The key thing is that this is exponential in c. So taking c equals to 100, it's tiny. This is really a minuscule probability. And if this is not small enough for you, you can go c equals to 200 or 300, and you're going to get a really, really tiny probability of a false positive. So if you're willing to have a very small probability of a false positive, then you have this very simple data structure, which just corresponds to having a binary string. It's very simple to maintain, and it's very fast query times, and the false positive probability is very small. The downside of this data structure is that occasionally you might have some false positives, and also it doesn't easily allow for deletions from the database. Though there are some heuristics for allowing deletions. These are modifications which are called counting Bloom filters. Well, that completes our description of Bloom filters. I look forward to seeing your projects where you're going to implement Bloom filters, and you're going to explore whether these approximations that we did in our analysis were reasonable or not. Let's summarize a few key points about Bloom filters. First off, let's recall the notation. Little n denotes the hash table size, and note that it's simply little n bits. M is the database size. This is the number of insertions into our hash table. And we use C to denote the ratio of the sizes. So C equals n over m, and this is at least 1. And finally, K is the number of hash functions that we're using. Let's recall what we proved about the false positive rate. For an element x, which is not in our database, so we never inserted it into our set S, what's the probability of a false positive, that we falsely report that x is in the database? Well, we proved that this is approximately 1 minus exponential of negative k over c, all raised to the power k. Well, this is a bit of a monster. What we proved is that for the optimal choice of k, this simplifies to 1/2 to the power c ln 2. Looking at 1/2 to the ln 2, this is approximately 0.6185 raised to the power c. And this is for the optimal choice of k, which is c ln 2. Now notice this may not be an integer value, so we may not be able to achieve exactly this false positive rate. We might have to look at the closest integer. Now there are a few issues I'd like to point out. First off, this is not a rigorous bound. This is simply an approximation. What was the approximation we used? Well, we replaced 1 minus x by e to the minus x. Now for us, x was 1 over little n. Well, if we look at this for big N, then x is tiny. And when x is small, this is a good approximation. So this was a reasonable approximation. So we do expect the false positive rate for these hash functions to behave like this. The big issue is that we assume these hash functions are random hash functions. So for each element x in the universe, their hash values are mutually independent of each other. Now it's impossible to use such a random hash function. And the question is, how does an actual implementation of a hash function compare to this theoretical results for this random hash function? And that's what you're going to address in your project. For a simple choice of a hash function, h, we're going to compare the actual false positive rate for this simple implementation of a hash function, and we're going to compare it to the theoretical false positive rate, which we predict for a random hash function. So it's a quite intriguing question. If we look at an actual hash function and we look at it as a function of k, does the actual false positive rate behave similar to this theoretical result? And does it turn out that the minimum false positive rate occurs at k equals c ln 2, or the closest integer to it? Now there's quite a lot of design choice you can use in your choice of a hash function, and we're just going to use a simple hash function in order to simplify this comparison.